DeepSeek just released a physics simulator that can predict molecular behavior so accurately, it's making researchers question whether we actually understand how these systems work. And I'm not exaggerating. This is genuinely worrying some of the smartest people in AI right now. So what exactly did they build, and why should you care? Stick around, because by the end of this, you'll understand why a tool that's supposed to help us might actually be revealing a blind spot in how we think about artificial intelligence itself. Okay, so first, let's ground this. DeepSeek is a Chinese AI lab that's been quietly building some seriously impressive stuff. They're the same team that released DeepSeek v3, which basically matched GPT-4 and Claude in a lot of benchmarks while being way cheaper to train. But this physics simulator, called something like their molecular dynamics model, that's a different beast entirely. Here's the core idea. Physicists have spent decades building mathematical models to predict how molecules move and interact. These models are based on actual physics, Newton's laws, quantum mechanics, the works. They're not guesses. They're grounded in our fundamental understanding of how the universe works. When you want to simulate how a protein folds or how a chemical reaction happens, you use these physics-based models. They're accurate, they're reliable, and crucially, we understand why they work. Now, DeepSeek trained a neural network, basically a giant mathematical pattern matching machine, to do the same job. No explicit physics baked in, just data and training. And here's the thing, it works. It predicts molecular behavior with accuracy that's competitive with or sometimes better than the traditional physics-based models. That sounds like a win, right? And in one sense it is. If you're a drug company trying to simulate how a molecule behaves, you don't really care if it's a physics equation or a neural network doing the predicting. You just want the right answer fast. But here's where the terror comes in. When a physics-based model makes a prediction, you can trace back and ask, why? You can point to the equations, the constants, the principles. You can say, here's the mechanism. Here's what's actually happening. It's interpretable. It's auditable. If it fails, you can figure out why. When a neural network makes a prediction, you can't. Not really. You can feed it inputs, watch the outputs, maybe run some statistical tests to figure out which features matter most. But the actual reasoning, the path from input to output, is locked inside millions of parameters in a black box. You can't open it up and see the physics. So the question researchers are asking is, what is this neural network actually learning? Is it learning a compressed version of actual physics that it can then apply to new situations? Or is it learning statistical correlations in the training data that just happen to work on the test set? This matters because of something called generalization. Physics-based models generalize beautifully. You learn the rules once, and they apply everywhere in the universe. A physics model trained on one type of molecule can confidently predict behavior in completely different molecules because the underlying principles are universal. But neural networks? They're brilliant at interpolation, filling in gaps between training data, but they can be fragile at extrapolation. They can fail catastrophically when you push them even slightly outside the distribution of data they were trained on. If DeepSeek's simulator is learning correlations rather than principles, it might nail predictions on molecules similar to its training set, but completely bomb on novel chemistry. And here's the scary part. We might not know which is which until we deploy it and it fails in the real world. So why are researchers actually terrified? It's not because the AI is too dumb. It's because it might be too good at looking smart without actually understanding anything. It's the old AI problem. You can build something that passes all your tests and still have no idea why it works or when it will fail. There's also a deeper philosophical angle here. For centuries, physics has been about reverse engineering the universe. We observe nature, we build models, we test them, and if they work, we feel like we've uncovered something true about how reality works. But what if we can just train a neural network to predict nature without ever touching the underlying truth? What if prediction and understanding are totally separate things? This is actually a big deal for the future of science itself. If AI can predict physical systems without needing to encode physics, what does that mean for physicists? Are they still needed? Or are we entering an era where we get good predictions but lose the ability to actually understand how things work? Now, to be fair, this isn't a totally new problem. Physics-based neural networks exist. Researchers are working on hybrid approaches where you build in known physics as constraints and let the network learn the rest. And some labs are making real progress on interpretability, understanding what neural networks actually learn. But DeepSeek's result is a wake-up call. It's showing that you can get shockingly good performance on real, hard physics problems without explicit physics in the model. And that's forcing the field to reckon with some uncomfortable questions about what intelligence and understanding actually mean. The other thing that's making people nervous is the pace. DeepSeek is moving fast. They're open about what they're doing, and they're making breakthroughs in areas where people thought you needed way more computational resources. This simulator might not be the most powerful physics model ever built, but it's efficient, it's accessible, and it works. That's a combination that tends to get adopted quickly, regardless of whether we fully understand it. So what does this mean for you? Well, if you're in drug discovery, materials science, or climate modeling, this is relevant. These are fields where physics simulation is a bottleneck, and tools that can speed up prediction, even black box tools, are valuable. But it also means you need to be more careful about validation. You need to test these systems harder. You need to understand their failure modes. More broadly, this is a sign of where AI is heading. We're building systems that are genuinely useful and genuinely inscrutable at the same time. And we haven't really figured out how to handle that yet. We're in a period where AI is outpacing our ability to understand it. And that gap is where a lot of the real risk lives. The physicists aren't terrified because DeepSeek's simulator is going to destroy the world. They're terrified because we're building tools that work, so we might stop asking why they work. And that's actually a profound shift in how science operates. If you want to stay on top of breakthroughs like this, the ones that actually matter, not just the hype, subscribe. I break down the stuff that's reshaping AI and tech every few days, and I skip the noise. Thanks for watching.